Sure. Good evening again, everyone. I wasn't expecting me to be the first one again, but thank you for giving me this opportunity. And to be very honest, currently I am a part of minor in quantum technologies here in NIT, and I always had this curiosity of merging material science and quantum computing. And this course did give me an opportunity like this, and to be very happy, this same presentation, just in a more quantum mechanical perspective, I'll be giving again in the quantum computing minor for their internal evaluation. So there, if you want, you can of course join there. Everyone's welcome there also on 22nd and 23rd of this month from 10 to 11 a.m. So going on to what we are trying to do here, we are trying to merge quantum computing with material science. And as we do start, where is the motivation for the problem? The motivation for this problem is the quantum, or the computing complexity. This is where the quantum part of the problem comes in. When you are trying to model 10 to power 24 atoms, you have interactions 10 to the power 24 into 10 to the power 24 minus 1 for 2 atoms if you want to model. And if you are trying to understand the interaction between all the bodies that are there, or the molecules, then this will be a factorial of this, right? So if you are modeling such a big number, as we know, it is more than an exponential increase. So this is where the quantum comes in, and it makes the life easy for us. And the kind of quantum computing that we see in currently, there's a recent procurement of a quantum computer by SRM University in Hyderabad, and yeah, they are working with TIFR Hyderabad in developing one for India, and anyone in the world can access that for betterment of science and research. So yeah, with this background, let us first, I felt like we should deal with the mathematics of the stuff, and at the end of the problem, we'll discuss where the quantum part comes in. Because if we are firm with the materials part of it, then it will be easy for us to know how it is. So yes, so let us start with the mathematical foundation. So this is a typical approach that a scientist does when he or she is trying to model the quantum effects in a molecule. On the left, you can see that you do the chemical system, you determine the types of bonds, then you do a mathematical representation. And I don't think we are much aware of the Hamiltonian. So if you remember the Schrödinger wave equation in your first semester, it is H psi is E psi. This is the Schrödinger time independent wave equation, where this is your operator, Hamiltonian. That operator is an energy operator in which you express the total energy of your system, and as it is an operator, of course, in quantum mechanics, everything is matrix. So we'll be dealing with a lot of matrices and linear algebra now from the next slide onwards. So just to give an idea, we are building the Hamiltonian of a system, and Hamiltonian is the total energy. Let us say we have a free falling ball from a height h. So the energy would be mgh plus half mv square. This is your Hamiltonian for that particular object. The ball that's freely suspended and falling down. Now, if we start writing things down in vector spaces, like velocity in vector spaces and this, so this will become an operator which we call in quantum mechanics. And of course, then as we have seen in thermodynamics, that we use the Einstein's picture, and we found out that h nu 1 lambda plus 1 by 2. This was the energy that we used there, and this all came from this Hamiltonian itself. Like if we want, we can of course discuss in person regarding how we are getting this energy state and all these things. Because once you define Hamiltonian as a matrix, every matrix has its eigenvalues, eigenvectors. So energy is the eigenvalue, and eigenvectors are the corresponding eigenstates of that particular energy. So this is the eigenvalue for which there will be a state of energy. Like we say, a very big example can be your atom is in kth shell or L shell or M shell. So these are your energy values, and your atom or electron orbiting in that particular shell is its eigenstate or eigenvector. That's what we can say. So if we are trying to model it using a quantum computer, you go to Hamiltonian using a quadratic unconstrained binomial optimization. Okay, so I can understand these are a lot of tough words together. So we'll deal with them in the upcoming 2 slides. I promise we'll understand each and every word of it and why we are dealing this. So we can assume this is like a particular operation or an algorithm that we have developed for solving. And once you know your optimization principle, it's again you are boiling down to Hamiltonian. And once you know your total energy of a state, you can again find out the eigenvalues and eigenvectors, and then you can simulate your particular model. So with this, let us now see these 2 models, Ising and quadratic unconstrained binomial optimization. So Ising model, I hope you all, if you are a physics geek, have heard in magnetism. So this model is very much in use not only in magnetism but also in finance, politics, and any other branch where you can see a domain orientation. So what it does is, let us say these are your different, this is your material, and if you have applied an external magnetic field, let us say B, so how much will this domains orient in that direction is computed using this model. So now you can see there are 2 summations and these 2 different terms. So let us understand what these terms mean in a very superficial way. So the first term that we have, not to get the location wrong, is HISI plus summation of JIJ SISJ, and here we have ING summation and here we have. So yeah, another thing will be dealing summations like this. The upper limit is of course known, it would be the total, and the summation is number at the bottom is the one that we are doing the iterations for. So here it's I, so INJ, it means there's a double summation here which we are writing INJ. So we are following the Einstein's summation principle here. So we won't be writing double summation, instead we'll be writing 2 notations at the bottom, just to make everyone clear that these are the 2 summations. So what is this? This term is the particular system or a particular electron spin being oriented in one direction, and this is the interaction parameter. As you can see, there is an INJ. So what this means is that, let us say if we have, let us see this 6 atoms, or let us say 6 domains of magnetic field, and we are applying a magnetic field outside, and now each and every domain will have its own bias, which we call HI. Its own bias is HI, and this is the interaction parameter. So let us say 1 as the nearest neighbors, 2 and 4. So what will 2 and 4 be having an effect on 1? So that let us say if 2 is oriented in this direction and 4 is also oriented in this direction, and 1 is oriented backwards, let's say, and the magnetic field is this way. So these will orient themselves in a way, and they will influence 1 to change, right? So they will make 1 to change its domain either here or here. Somewhere that will be decided by this way, how much it will align in the direction of magnetic field because of 2 and 4. Similarly, now we can have an array of atoms, an infinite array of atoms, and we can use this problem, use this equation here to solve the problem. But again, what happens is, this is a model developed by physicists, and if you can see here at the bottom, the quadratic unconstrained binomial optimization model, also looks the same if you see. We have these same terms, SI and XI, and these interaction parameter terms. The only difference that we have is the limits, like SI can take values +1 and -1, and here I can take the values 0 and 1. And here now we are trying to write it in matrices. This is the only change that we have done. And now that we have the power of linear algebra, and you all know matrices can be computed very fast. Matrix multiplications and matrix operations are very easy and optimized on a computer. That's why you can now have this, and this is a model that we'll be using, and you will see this image recurring in the presentation ahead. So these are 3x3 supercell of 18 sides, and each and every one of the circles you're seeing is a carbon atom here. So now we'll be modeling the vacancies using this, which is the topic that I've written. So now we are going to start with the quadratic unconstrained binomial optimization. These 4 terms we'll try to analyze in the next 2 or 3 minutes. So we are having, let us try to dissect the terms. Quadratic, that means there will be a square term, an x square term somewhere. Okay. Unconstrained, that means there are no constraints put on the system currently. Binomial means it can have only 2 values, which we are restricting to 0 and 1. And we are optimizing this function. This is the meaning of the terms. So now let us try to solve this simple problem immediately, because if we solve this problem, we'll understand. This is a very good problem from combinatorics, that is called max cut problem. Now if you want to have a cutting plane through this system that is connected like this, and you want the maximum number of output on both sides, like maximum number of atoms on one side of the plane and the other side of the plane. So how will you model this using QUBO? We'll be calling this QUBO, because once we define a thing, we name it, we own it. So we'll be owning the term by saying it QUBO. So we have to illustrate this problem of max cut. We will be putting down our weights, and I'll immediately show the solution, because then it will not take a lot of time. So this is the equation that we have written. So we are having 2, like as the problem had in the previous slide. Here we have the 1, 2, 3, 4 and 5, and 1 is connected to 3 and 2. So in such a fashion, we'll be writing this equation here, where you can see we have 2x1, 2x2, the individual biases, and also we are subtracting the external biases because of the combinations. And we will then, so I'll write how that equation came on from. So this is your y, which you're writing as x1 minus x2 the whole square plus x1 minus x3 the whole square, and so on. How are these terms coming? I'll show again. So here is your plane, and if you are cutting it, and if you are adding the 2 x's, like here there's x1 and here there's x2, and if you randomly add this xi through the cutting plane, so xi plus xj should be equal to 1, because if you are cutting it, and we are assuming that the plane on the ones on the left side are 0, on the right side are 1 of the plane. So on the right side, if let's say xj is coming, then it will be 1, and if xi is coming on the left side, it would be 0. So this addition would be 1, and its subtraction would also be not 1. So we will square it out, because we want quadratic terms for our optimization principle. So we square it out, and now we start writing the equation, which is between 1 and 2. So we write x1 minus x2 the whole square. Then we are between 1 and 3, so we write x1 minus x3 the whole square. Between 2 and 4, so we write x2 minus x4 the whole square. Between 3 and 4, and 5 and 4, and 5 and 3. So we have to write each and every parameter, and because of that we get this equation. So now simplifying it out, you know that we are having quadratic terms, that is xi is equals to xi square, because we are having 0 and 1. So your xi can be replaced by xi square, and that's where the power of matrices comes in, and you can write it in this way, because then you have a square power, so you can write x transpose x and your q. So once you have q, you can use all the possible values of x. Let us say we have this 5 values, so 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, all this, and you can compute and find the optimal solution, and you get this one. So this was one of the examples, and running very fast ahead. These are the penalty functions, that these are the constraints. If you can see on the left side, we have classical constraints for a particular graph and how you can model them. So this penalty P is the weight of the field. Like you can have an arbitrary value assigned, and you can inculcate this within your Hamiltonian or QUBO of that system. So one such example, if I have to fast go ahead, is again the same one. But now, if I say we wanted a minimum vertex with a constraint, a minimum vertex to cover. So in such case, we would have to use our penalty function as well. Here, just grazing it very fast because I'm the later time. So with such edges, now I'm writing the penalty function. This is just a constant p, and I'm writing it down. Again, I simplify the equation that I have to minimize. I write it in terms of x and x, x1, x2, and then I replace the single terms with x square. And once I replace it with x square, I again write it down in x transpose qx, and I get the value of q as minus 45 and x as this. So what I'm trying to do here is just finding the values zeros and ones, where 0 is there is a vacancy and 1 means there is an atom present. Now we have to see it like this. So coming on to single vacancy structure, very fast, like we model the same equation that we have written, summation si xi plus summation gij xi xj. In this, now if I put in the weights, and this is just what I told you, we are trying all the binary values and we are trying to get the output. And you can see these are arbitrary energies we have assigned. Like if there's no atom, then we'll have a -1. If we have atom, then we'll keep 0. So you can see in one vacancy structure of graphene, the one we have shown here, you have the energy as same. So these all are degenerate states. And here is the two vacancy structure. This would be more clear now, because with two vacancies in this particular unit cell, if we have to say, there are two vacancies, 1 and 2, and this is again another unit cell. The same vacancies are repeating because this is a periodic boundary condition. So you can see this configuration has -21, and this is the one with the least energy. So this is the most optimum solution. And coming down to how to implement this in quantum computing. So this is a bit above the head, I'll say, but still I'll be covering it. So what happens is, now you have to correlate each and every atom that you are writing in matrix form to a physical qubit. And once you are implementing that, you are getting this kinds of entanglement and operating structures, which you can see here. And just show, like, these are the physical qubits that are present in your QPU, quantum processing unit. And you are optimizing the solution by doing processing on these qubits. These are for 1, as you can see here. The mapping vacancies were done for a lot of problems. Vacancy free structure, and C and D. These represent for one vacancy structure. So you have to use these many qubits, the physical ones, to simulate this kind of problems. So now coming very quickly onto the quantum side of the part. You can see here this is a quantum computer, and at the end you have a Josephson junction where the computing takes place, just to keep a picture of what it is. So if you have to understand quantum computing, you have to look at this. How and why is the quantum processing or optimization faster? Because if we have two minimas, let us say you have a curve like this. So you are going from one point to another computing. But when you have a quantum state like this and you are over here, you can directly tunnel to the next state and the next state finding the minima. This is a much faster approach. And here we use the superposition principle and quantum tunneling to use this, because there is a probability that your state will go in that particular state. And we have to do this a million times to do this kind of simulation. So this process what we are doing is called as quantum annealing. That is, we are lowering down our temperature, but we are going down for a minimum, like similar to the annealing that we do in our mechanical processing. So this is the pipeline. Like this is a paper that I have been referring to. If you are very interested, it is from the Journal of Applied Physics, and the author is B. Camino, and he is a London-based researcher, and he's very much working rigorously in chemical quantum computing and the chemistry behind how you can model these things. So you can also check his GitHub page out, because he has good repositories for this. So yeah, looking at this, how you can convert your chemical system into a quantum system. So as we were doing this kinds of mathematics here, initially you have to decide your atoms and your periodic boundary conditions. Then we decide our vectors, graphs and binary states. You write your QUBO or Hamiltonian, and then you correlate it with your quantum state, and then you optimize it using quantum tunneling. That's how this whole process occurs. So this is just a way of converting Ising model to QUBO model, and this is again a correlation that I was talking about, minor embedding. So this is your graphene structure, but each and every atom here, each and every bond here corresponds to one of these input parameters, and these are connected to each and every output parameters, and they are a neural network, you can say. Each and everything is connected, and the weights are to be adjusted accordingly. It is an again optimization process. So yeah, this is quantum annealing, where you have your initial state and your constraint. So with time, your alpha goes on decreasing and your lambda goes on increasing. And this is again the minor embedding which I was talking about. You can see now clearly. These on the right are your qubits, physical qubits, and on the left is your mathematical model which you are correlating with using mathematics and computing. And yeah, so now discussing the most important part, where will this be implemented and how can we go ahead in this? So these are some of the examples of what the paper talked about and what more can be done. So now we simulated vacancy, but we can also go for simulating solid solutions where there is someone else sitting in the interstices somewhere. You can see nitrogen dope, graphene, and other stuff, as we discussed in our class as well. So such kinds of precipitates can also be modeled, and yeah, this is a very interesting and booming field, to be very honest. And so yeah, I mean, the last slide was a QR where I had all the repository in. So maybe I'll just share this link in the in our group, because I wanted, like, this is a very booming topic, and the research, I mean, I was behind this topic for like last 2 months, and it is a very interesting topic. I feel that I have tried to deliver something out, but I also am not a very good understanding of what it is, and neither I feel like you have also just understood the gist of what the thing is. So just I wanted to interest you in this small topic, and at the end I would like to say that Srivastava sir has been very pioneering personality in my life now, especially from thermodynamics, and that was the acknowledgement slide. So and not only him but other professors as well, but the most favorite thing is the mathematics that he tries to do with rigor, which I feel that I try to do justice in my topic as well. So if I have not, then please do apologize me, and there might be mistakes here and there. We'll correct and learn together in this topic. So that was from my side. Thanks a lot.